Hi. Starting from today, I will teach the remaining of the semester. So we will first of all do chapter 6, and then we will do chapter 10. Of course, we will not be able to cover all the sections in chapter 10, just a few sections to give you a taste for the partial differential equations. So we will start with chapter 6, and which is about the Laplace transform. So basically, for the remaining of the semester, we will learn two integral transforms. And these are going to be our main techniques to solve the differential equations. We will use the Laplace transform for solving ordinary differential equations, ODEs, with initial values. And we will use the Fourier transform to solve partial differential equations. Okay, now let's start with the chapter 6, which is Laplace transform. All right, so what is a Laplace transform? This is an example of an integral transform. So we use integral transforms to transform functions in one domain to another domain. And we gain some new techniques and which will help us basically to solve differential equations which we were not able to solve, or we will use them to solve the differential equations in a quicker way. And Laplace transform is one of them, and we use a certain function and which is called the kernel, and to transform the functions. So what we are going to do is basically the following. So we will have functions, derivatives, which are given as a function of time, and we will transform them. We will transform them to some other functions, some other maybe derivatives or whatever, by using this transform. So I will use the letter L for the Laplace transform. But now the new variable will be the S we are going to use. So this is the S domain. So what we are going to do is the following. So we will have a function, and this function will be typically defined for t bigger or equal to 0. It can be just bigger than 0. You don't need to worry about the for finitely many points, because it's an integral transform. So by using this, and we will get another function here, which is now a new function. And what is the definition of the Laplace transform? So it's an integral transform, as I said. So we will define it in the following way. Definition. So Laplace transform of a function f is defined as the following. Okay, from 0 to infinity, e to the minus st times f of t dt. Okay, so here f of t is the function, and it is defined for t bigger or equal to 0. Here, this function, e to the minus st, is called the kernel of this transform. Okay, this is called the kernel of this transform. Basically, I mean, integral transforms are similar, but for each transform, the kernel will change. Here we are using an exponential function, and later for the Fourier transform, we will use something else. Also, and as I said, and we are talking about a function defined for time bigger or equal to 0. You don't need to worry about, again, for finitely many points. If it is not defined at finitely many points, we don't care, because you are basically integrating. So, integral will not care about finitely many points. But there is one issue here for this Laplace transform, and this is an improper integral. And we know from calculus, this integral may converge or may diverge. Of course, I mean, when we are talking about in a Laplace transform of a function, we will assume that, I mean, Laplace transform exists whenever this integral converges. Also, for which s values the integral converges will determine the domain of the Laplace transform. So, and this we are going to use f of s for this, because here you are integrating with respect to time t, and then so if you evaluate, eventually it will be a function of s, and that then the domain of the capital F, which is the Laplace transform of small f, will be basically for which values of s this integral is convergent. So again, now first of all, our function must be defined for time bigger or equal to 0. We are not talking about the previous part less than 0, and this integral must converge. Of course, I mean, there's an issue here. For not every function this integral may converge. So for those, of course, we will not be able to find a Laplace transform. All right, so I will start with an easy example, and along the way we will do tons of examples. We will transform lots of functions, and later we will learn how to transform derivatives, because at some point we need to solve differential equations. At this point, I want to say something. We are going to use Laplace transform to solve initial value problems. Whenever you are given just a differential equation without any initial values, you won't be able to use the Laplace transform, and you will see this in the upcoming lectures. Okay, so this is our definition, and now let's see our first example for the Laplace transform, and we will start with the easiest function, and that is the constant function 1. So our first example is f of t is equal to 1. So for t bigger or equal to 0. So what is the Laplace transform of this? Okay, let's now compute f of s, which is the Laplace transform of f. By definition, as you see, from 0 to infinity, e to the minus st f of t dt. So I need to evaluate this improper integral. So then what we are going to do, so as you remember from calculus, so we first of all write it as a definite integral with a finite number a, and e to the minus st. Now, in this case, f of t is going to be just 1. And then I will take the limit as a goes to infinity after computing this definite integral, which will depend on a. So it's a very easy one. So we can handle it here. Limit a goes to infinity. So what do we have? We have the antiderivative, e to the minus st divided by minus s. And our bounds are 0 and a. Okay. So if you look at, this becomes limit as a goes to infinity. So we have now e to the minus s times a over minus s, and minus 1 over minus s, because e to the 0 is 1. So this is what we have. Now, what do I want? I want this limit to exist, and so for those s values, and I will be able to compute the domain of the Laplace transform. All right, so now let's look at, so I'm taking the limit as a goes to infinity, so there is no a here, so this part is okay. This is just 1 over minus s. But now there is an a here, so if you look at, how about the limit of this one? So actually there are two issues here. If a is, as you can see, now a is here, positive. And so if this product is positive, we know that exponential function will go to infinity. So then there is no way for this part to converge. This limit will go to infinity. So that means that this product must be negative. So then exponential will go to 0. So that means here for this limit to exist, and which also means this improper integral converge, we must have S positive. So if S is positive, A is positive, this product is negative, so it will go to 0. If this part then goes to 0, then the limit will be just the remaining part, which is just this portion. So then this answer will be 1 over S. So then what did we learn? The Laplace transform of the constant function 1 is equal to 1 over S. So let's write it here. And this is our first, basically, formula. So Laplace transform of 1 is equal to 1 over S, and this is true when S is positive. So we were able to now transform the constant function 1 by using this Laplace transform. So the Laplace transform of constant function is 1 over S. Okay, this is what we did first. Now let's do one more example, one more simple example. Let's do the exponential one. Okay, so now second example. Now this time it is the exponential function, e to the at. Again, we have t this, right? So again, now I will just write the formula. I'm taking the Laplace of e to the at. So this time I will be quick, so you got the notion of how we are going to compute. So I'm writing from 0 to a, e to the minus st, e to the at dt, and after this I will take the limit as a goes to infinity. All right, so both of them are exponential. I can put them together. So then this time from 0 to a, and this is minus parentheses s minus a t dt. Now it became similar to the one case. So if you do this as a goes to infinity, antiderivative is going to be e to the minus s minus a t over minus s minus a, and with the limits of the integration as 0 and a. And from this, if you write it again, so we will have e to the minus s minus a times capital A over negative s minus a minus 1 over minus s minus a. Okay, this is what we have. And actually, I mean, this is similar to the previous example. So again, there is no capital A here, so this limit of this part is itself. And so as a goes to plus infinity, I want this part to converge. Again, the exponent must be negative. To achieve this, since I know capital A is always positive, as we can see from the limit, this part s minus a must be positive, so eventually the exponent will be negative, so it will go to 0. So then this can be achieved only when s minus a is positive. In other words, s is bigger than a. And then what's going to happen for the limit? Again, this part will go to 0. That's the only alternative for the convergence. It cannot converge to any other thing. Either it goes to infinity, which is what we don't want because we want convergence, or it will go to 0, and in that case this part will be 0, and eventually negative negative we will get 1 over s minus a. Okay, so Laplace transform of the exponential function e to the at becomes 1 over s minus a, and this is true when s is bigger than a. Okay, all right, so now we learned two formulas right now. We know how to transform the constant function 1, and we know how to transform the exponential function e to the at. Okay, so let's write the second thing here. And that is Laplace transform of e to the at is equal to 1 over s minus a, and this is true when s is bigger than a. And actually, I mean, you can see this is like a shifted version. 1 over s minus a is a shifted version of 1 over s. Okay, so I just now we saw two examples. We will continue with one more example, which is a little bit more complicated than these, but at some point I want to do it. So why are we doing this, and what do we gain? So as you can see, like from these examples, one is constant function, and exponential is an increasing function or decreasing function, whatever, depending on a, of course. But we transform them, and we got 1 over s and 1 over s minus a. And also you will see one more thing, and all these things are going to be, in our examples, like partial fractions, expressions like in the rational form. And so basically that's the idea of the Laplace transform. So when you start transforming your functions and later your derivatives, from a differential equation you get an algebraic equation. So in the t domain you have a differential equation, but when you go to the s domain you will have an algebraic equation. And algebraic equations are easier to solve. And then when you solve them, then you can solve it in the s domain, and then you can come back to the t domain and you will eventually find the solution. All right, that's the idea. So from a differential equation we will get an algebraic equation by using the Laplace transform, do everything in the s domain, the algebraic way, algebraic solution, and then we will come back. So how we are going to come back? Of course, I mean, later we will see there's an inverse process. You will go with the Laplace and you will come back with its inverse. Okay, so, and one more thing I want to mention, this transforms, Laplace transform and the Fourier transforms are used a lot, especially in signal processing. So you can consider like a 1 e to the at or generally f of t as a signal. So you have a signal and transform, Laplace transform later, the Fourier transform transforms it to a different signal. And you will work with that signal and then you will eventually come back. So, and if you look at, I mean, here, in the time domain, we had a constant signal. Okay, so this is constant. So this is f of t. And we applied Laplace transform to this, and we got 1 over s. So this is the f of s. So we started with a constant signal, and then eventually Laplace transformed it to a different signal. But now here, it's the time domain. Here, it's the s domain. So different domains. So Laplace transform a signal to a different signal, and then you will do everything here, and eventually we will go back. So by just looking at the signal, we know where it came from, and by knowing that one, where it came from, we can come back. All right. Now let's continue with one more example. That is the, let's do the sine, and then we can easily do cosine later. So by the way, I mean, we will learn lots of functions, Laplace transforms, and also we will learn the properties of the Laplace transform, which will help us. And at this point, maybe I want to say something about it. So in the old books, in the 9th edition, there's a table. There's a table in 317. In the new edition, I just printed it. In page 252, there's a table, and we will be able to finish almost all the entries in this table, and we will learn the Laplace transform of almost everything we are going to use. All right, now let's do one more, and this time I may write a little bit smaller because it's not as easy as these ones. It's not complicated. I mean, it's not very difficult, but I need to do integral very carefully. So now this time my signal is the sine signal, sine AT, and let's see what is going to happen for this signal now. Okay, sine AT Laplace. So limit as a goes to plus infinity from 0 to a, e to the minus st sine at dt. Okay. Now I need to compute this antiderivative. You remember from calculus, this is a classical example of an integration by parts, where one of them is an exponential, the other is a sine. And if you remember this example, I have to do integration by parts twice to evaluate this thing. So let me do it the following way. Let me first of all compute the antiderivative and eventually compute the limit here. All right? So so what is this antiderivative? So what we are going to use, again, integration by parts. If you remember, we have an exponential, we have a trigonometric, and so typically trigonometric comes first, exponential comes the last one. So I will say this is my u, and this is my dv. So with this now, with this u dv from 0 to a, e to the minus st sine at dt. So u is equal to e to the minus. So I made a mistake, sorry. Actually, it will not matter here, but I would pick the other way. Just so I will pick this one as dv and this one as u. Okay. All right. So now let's see. We have sine at and dv is e to the minus st dt. Du is going to be a times cosine at dt, and v, the antiderivative, will be e to the minus st over minus s. So with this now, we have u times v, which is e to the minus st times sine at over minus s from 0 to a, and minus from 0 to a. Now we will have v times du. So I can take minus 1 over s out, so it will be plus 1 over s here. So we will have e to the minus st. And we have a here, so I can put a out. So cosine at dt. Okay. This is what we have. And again, we got exponential, trigonometric. I will use a similar formula. So again, let me just write. So u is going to be cosine at, and dv is going to be e to the minus st dt. Du is going to be negative a cosine at, and v is again e to the minus st over minus s. So with this now, I will rewrite this integral. And as I said, it is not complicated, but it takes some time so to compute it. And with this now, what do we get? We have e to the minus st sine at over minus s from 0 to a. And we have a over s parentheses u times v, which is cosine at times e to the minus st over minus s from 0 to a, and minus and v times du from 0 to a, and we have now minus minus, that's plus another minus here, so we have a over s e to the minus st and sine at dt. Okay. So then what did we get? So we have the same thing repeating here, and we started with the same thing, e to the minus st sine at dt. So we ended with the same thing. So as usual, we will take it to the other side, and then we will just group them together. And then on the right-hand side, we will just have this one and this one. Of course, we have to compute the boundary values at 0 and at a. So then what do we get? If you take this thing to the other side, we have one copy there, 1. And then we have minus a over s, so we have a square over s square with a minus. On the other side, it will be a square over s square from 0 to a, and e to the minus st sine at dt. And this side, we will have this one and that one. Okay, so we will have e to the minus st times sine at plus and a over s, there's a minus s here, and cosine e to the minus st times cosine at over, now this will go out, so I can write here negative s square with, and from 0 to a. Okay, so let's put the boundaries. So when you put a here, we will have e to the minus s times a sine a times capital A over minus s. and minus a over s squared and e to the minus s a cosine a times small a over, yeah, okay, I wrote it. This is the first part, and then minus of the integral. When you put 0, what do we get? When you put 0, so sine 0 is 0, so this is vanishing. When you put 0, cosine 0 is 1, e to 0 is 1, so we get minus a over s squared. So now let me just write it, plus a over s squared. Okay. Now what are we going to do? Of course, eventually we will take the limit of this part. Okay. So here, let me do just erase this portion. And what are we going to get? So we will take the limit. Maybe just for you to follow, let's take the limit here in the previous one and just write the answer there. All right, so eventually what will I do? I will take the limit as a goes to infinity. Again, for this portion, I mean, this part will just oscillate. But if this product is, again, positive, if this product is positive, then this oscillation will get bigger and bigger so that we won't have any limit. A similar thing will happen for this one too. Again, there is only one alternative for the convergence. If it's going to converge, it must converge to 0. And when does that happen? So this product is negative, which means s is positive because a is already positive. So this will go to, then this part will be negative. Eventually, exponential will go to 0. So you are multiplying sine. So sine will oscillate, but its amplitude will always get smaller and smaller. So which means this portion will go to 0. So again, this one, again, similarly, this will oscillate, but the amplitude will go to 0. So from this part, you will get this part is 0. Then what is left is just this, a over s squared. And so we have a over s squared as this one. But of course, there's this coefficient. I'm not computing the limit of, I'm not just computing this one. This one times 1 over a squared over s squared is computed. So then, what do we get as the answer? So I have to divide this thing by that one, which is going to be a over s squared divided by 1 plus a squared over s squared. So if you do this thing, so s squared plus a squared, and there is an s squared here, s squares are canceling. What do we get? We have a over s squared plus a squared. And when does this happen? We said that for this thing to happen, this product must be positive. And when is this happening? When s is positive. So s is positive. So we learned the third formula. We know now the Laplace transform of the sine function. Okay, so let's write it here for you. So Laplace transform of sine at is equal to a over s squared plus a squared. This is what we have. Okay. So at least now we know 3 formulas. We know how to convert the constant function 1, exponential function, and sine function. We will do cosine. We will do some more. But before we do one more example, let's talk about some convergence issues. So as we learned from the definition of the Laplace transform, it's an improper integral, and if this improper integral converges, then we have the Laplace transform. So otherwise, I mean, we won't have anything. So then, when do we have this existence thing? Actually, we have some powerful theorems, and which says us when we have a Laplace transform of a function. Now, I will state this and sketch its proof for you. Theorem. Right? I will just write from the book and explain one by one. Suppose that first, f is piecewise continuous. Piecewise continuous on the interval 0 to a. For any a, for any capital A. I will explain what piecewise continuous. Actually, probably this was mentioned in calculus, but we should again repeat it. Second thing, it says f of t's absolute value is less than or equal to k times e to the at when t is bigger than m. All right, so here, k, a, m are some real constants. Of course, I mean, because of this, real constants which are positive. Then, Laplace transform of f of s exists. And for s bigger than a. All right. Now, what does this theorem say? Your f is piecewise continuous. So now, I may use this very often starting from now on. So you can think like f is a signal. You have a signal which is piecewise continuous. Piecewise continuous means, so it is continuous everywhere except at finitely many points. As you remember from calculus, we saw certain kind of discontinuities. Removable discontinuity, jump discontinuity, and infinite discontinuity. So piecewise continuous means you only allow finitely many removable or jump discontinuities. So there is no infinite discontinuity for the signal f. So your function never goes to plus infinity or minus infinity. There may be some jumps, or there may be a hole on the graph of the function, but no infinities, no going to infinities, no vertical asymptotes. So it's piecewise continuous. And if you do this, actually what you do, you guarantee the integral. Because for the properties of the integral, we know that if our function is continuous, we can integrate it. And if it is piecewise continuous, again we can integrate it, because you can do like, if the discontinuities are like at b, then you can integrate from a to b and then from b to c. And for the ends, you can use depending on the ends, you can use the right limit or left limit while you are computing the integrals. So this is what it means piecewise continuous. Second, it says that your function is always less than or equal to a constant times an exponential. So this means that yes, your function can get larger and larger, but it is never faster than an exponential like this. So it will be always less than or equal to a constant times an exponential. This basically says, I mean, in mathematical terminology, it's an exponential order. This at most it has an exponential order. So this is happening when t is bigger or equal to m. Why not from the beginning? I mean, you are computing an improper integral. Who cares what's happening until m? Because until m, everything is definite. And the big portion is the tail from m to infinity. And from m to infinity, your function is never exceeding the exponential. But we know that for the exponential function e to the at, we already computed its Laplace transform. So there is a Laplace transform for this one. So which means that the improper integral for the exponential e to the at, it converges. So if this thing is, for this one, it's going to converge. So f is smaller than exponential, which basically says that if you use a kind of comparison test, so the improper integral of f will also converge. So this is basically the idea. So if you write this thing in the following way, so it's just a sketch of the proof. Just a sketch of proof. And basically what I'm interested in, computing this improper integral, and from 0 to infinity, e to the minus st f of t dt. All right. So if you look at the absolute value of this, from 0 to infinity, and which is less than or equal to from 0 to a, from 0 to m, e to the minus st f of t dt. Okay, and this is just a sketch. And from m to infinity, e to the minus st and f of t dt. This is what we have. And for this portion, from 0 to m, so it's a definite integral, piecewise continuous function, I can easily integrate, so there is no problem for this portion. So how about this one? So now I will use a comparison for this one. Okay, so comparison for that one. Let me just go back. I know it's kind of, at some point may not be easy to follow because I'm using just two boards. Sorry, I mean, camera is fixed that way. All right. Now, how about this? The important portion, m to infinity, e to the minus st, f of t dt. So this one, and this is less than or equal to, we can take the absolute value inside. Okay. From m to infinity. And now I'm going to use the exponential order business. F of t is less than k times e to the at for some a and k. And so this is less than from m to infinity e to the minus st k e to the at dt. Actually, there is no need for the absolute value because everything is positive here. So it's less than this. But this is exactly, if you look at this, I can take k out, and from m to infinity, and maybe I can write this way, and less than or equal to from 0 to infinity, not from m to infinity, and e to the minus st, and times e to the at dt. And this portion is the Laplace transform of e to the at, and as we know from the formula, it exists. So which means this integral is convergent. And so basically by using this comparison, because everything is positive here now, so these are positive, and so this is now positive. I took its absolute value. So since we have this one now, and positive, so by comparison with this, big one is convergent, small one has to be convergent. So as a result, this improper integral is convergent, which was just the tail of this thing, so the infinite portion of the improper integral. This is convergent. This is already convergent because it's definite. So this integral is then convergent. And so we have the Laplace transform of f. So piecewise continuous is necessary for computing the integral because we are computing an integral transform. And it's an exponential order, so we can compare with an exponential function. So that way we can be sure that it will have a Laplace transform. Okay, until now, what we will learn, we are going to use Laplace transform to solve differential equations. And Laplace transform is an integral transform. We know its formula, but it's an improper integral, and we care about the convergence of this improper integral. And this theorem I stated is telling us when at least it will be existing. And furthermore, you can think like Laplace transform a signal to another signal. In the time domain, you have a signal, you transform to a signal in the S domain. And at least, I mean, we know the three functions. We know the Laplace transform of constant function 1, we know the Laplace transform of exponential functions, and we know the Laplace transform of sine, right? So now we talked about the existence. Let's do one more example, and then let's look at some more properties. Okay, so we did a constant, we did exponential, and we did sine. We will do cosine later. It will be very easy after knowing some properties. And then how about t to the n, a polynomial? And 1 is a polynomial also, but it's constant. So let's do t to the n. Actually, I'm going to use this 1 there, like our baby polynomial. Okay, our example, f of t is equal to t to the n, and t is bigger or equal to 0. So t to the n is Laplace from zero to a, e to the minus st, t to the n dt. Okay. Again, exponential, polynomial, we are going to use integration by parts. I mean, there is no way to escape from integration by parts because there is a product here. So polynomial, exponential. So typically, we choose polynomial as our u and exponential as our dv. So if you do this, let me do the calculation here. So u is equal to e to the minus, sorry, I'm just t to the n and dv is e to the minus st dt, and du is equal to n times t to the n minus 1 dt, and v is, as usual, e to the minus st over minus s. So if you, with this now, if you do u times v, limit as a goes to infinity, u times v, we have e to the minus st, t to the n over minus s from 0 to a, and from 0 to a, e to the minus st, t to the n minus 1 dt. There's an n and minus, so I will take them. Sorry, this was a minus, and I will take n out. I will take minus s out. Now it becomes plus. But actually, if you look at this portion, this is just the Laplace transform of t to the n minus 1. Okay, so then I can write this limit in the following way. Limit as a goes to infinity, the first portion, e to the minus st, I can plug in a now, a to the n over, oops, let me plug in a here, over minus s, minus, if you plug in 0, I'm assuming like n is bigger than, bigger or equal to 1, because when n is 0, I know the answer, that's just constant function 1. So if there's a t here, eventually this will be 0. And plus. So I can rewrite this as a goes to infinity. I can replace a with the infinity. It will be exactly the Laplace transform of t to the n minus 1, just the formula. So it becomes n over s times Laplace transform of t to the n minus 1. So now let's talk about the limit here. And this limit, a to the n, again, for this portion, we have two alternatives, either 0 or infinity. And this will always go to infinity. So if both go to infinity, then there is no convergence. If one of them goes to 0, then we can talk about this. So this will always go to infinity. Then when s is positive, this part will go to 0. We have a 0 times infinity. And this is like one of the cases in the L'Hopital, 0 times infinity. But then what we do, then we can take e to the minus sa to the bottom. So top goes to infinity, bottom goes to infinity. So we have an infinity over infinity situation, which allows us to use L'Hopital's rule. But after taking, applying L'Hopital rules a couple of times, depending on n, of course, you will see like the degree of the numerator, it will get less and less. But because the bottom has an exponential, it will always be an exponential. So there will be always an exponential in the bottom. And so eventually you will reach a constant function after taking derivatives, enough derivatives. For the numerator, the bottom will be an exponential. So top will go to a constant, bottom will go to infinity. So eventually, as a goes to infinity, this portion will go to 0. So that means that for the convergence, when s is positive, this part will go to 0. So this part will go to 0 when s is, this limit is 0 when s is positive. Okay, so then what did we learn? Actually, we learned a formula to relate the Laplace transform of t to the n to the Laplace transform of t to the n minus 1. So then we have the following. Let's write it here. Laplace transform of t to the n is equal to n times, n over s times Laplace transform of t to the n minus 1. Now, an inductive formula, so we can, now after this, we can derive the others. For example, what is t? What is t squared? What is t cubed? So Laplace transform. So then Laplace transform of t, which is the power 1, and that n is now here 1, we have 1 over s times Laplace transform of t to the 1 minus 1. Now this is 0, t to the 0 is constant function 1, and we know it's Laplace, which is 1 over s, so we get now 1 over s squared. So Laplace transform of t is this one. Furthermore, now Laplace transform of now t squared, let me just do one more. So now this is now 2 over s and Laplace of t to the 2 minus 1, it's Laplace, and if you write it, then we have 2 over s, 1 over s squared, so we have 2 over s cubed. Let's do one more, t cubed, then we will have 3 over s times Laplace transform of t to the 3 minus 1, and so we will have 2, 3, we have 3 times 2 over s cubed, s, we will have s to the 4th. So when you go t to the 4th, then there will be a 4 coming here. This time product will be 2 times 3 times 4. And as we know now, this is a factorial formula, and now from this we can easily write the formula for t to the n. So if you look at the formula for t to the n, we see that t cubed, 3 factorial, 2, 2 factorial, 1, 1 factorial. So the top is always n factorial, but bottom is t cubed s to the 4, t squared s cubed, t s squared. So s to the n plus 1, as from the derivation, this is when s is bigger than 0. So now we know constant function 1, polynomial, t to the n's, exponentials, and sines, Laplace transforms. Okay. Now, I will do one more property and an example coming from this property, and then maybe one more property, and then we can finish the first lecture. Actually, there is no proof needed for the first property because it's obvious. It's an property of the integral. So first property is an obvious property is Laplace transform is linear. So we can state as a theorem. So a times f of t plus b times g of t, Laplace transform of this is equal to a times Laplace transform of f plus b times Laplace transform of g. Okay, so how do we know? Because it's integral. Proof, very short. Of course, we are assuming that f and g has a Laplace transform here. So a times f of t plus b of t, v times g of t. So this is just from 0 to infinity, e to the minus st, a times f of t plus b times g of t dt. So I can multiply and then separate. I think there is no need to write it. Okay, so just property of the integral, we get that integral, the Laplace transform is linear. And so this way, I can do tons of things, at least for the linear combinations. So now, since I know t to the n, I can do a very simple example just for the sake of completeness. Now, I can take the Laplace transform of 3 minus 4 t squared plus 5 e to the negative t plus 3, 4, 5, let's make it 6 maybe, 6 times sine pi t Laplace. Okay, so now let's compute the Laplace of this. So I can do one by one. Now, what is 3? Actually, 3 is 3 times 1. So I can take 3 out. So I can put a 1 here if you want. And 3 times 1. So Laplace transform of 3 is then 3 times 1 over s minus 4 comes out. Laplace transform of t squared, t to the n formula. So we have 2 factorial, which is 2 divided by s cubed plus 5 e to the minus t. So minus t means a is negative 1. So we have just 1 over s minus minus 1, which is s plus 1. And then now we come to this one. 6 comes out, sine pi t. So pi is here our a. We had the formula a over s squared plus a squared. So pi over s squared plus pi squared. So with the property of the Laplace transform as being linear, so we were able to do this. So how do? We do piece by piece. And somehow we have to memorize the Laplace transform of these functions, polynomials, exponentials, and sine. All right. And one final thing, and then I'm going to finish the first lecture, which is basically, I'm done actually. I'm done with the first section, 6.1 actually, and I did something more than 6.1. I did some further formulas from the remaining sections and some exercises. So you can think this as in like property 2. I want to do this one. So actually I somehow mentioned it implicitly. If you look at this one, this is 1 over s, e to the at is 1 over s minus a. So I can think like this one is, it's like e to the at times 1. And if you multiply the function 1 with e to the at, as you see, like 1 over s becomes 1 over s minus a. So there is a shifting in the s domain. So now this is basically the property we are going to mention. So if you multiply your signal f or your function in the time domain with an exponential, this will correspond to a shifting in the s domain. So this is what it says. So this is equal to f of s minus a. So what is f? F is the Laplace transform of small f. So where f of s is equal to f of t Laplace. Okay, let's prove this thing. So what is the Laplace transform of e to the at times f of t? And this is from 0 to infinity, e to the minus st, e to the at, f of t dt. And if you write this, so you can group these two exponentials, e to the minus s minus a and times f of t dt. Now, if you remember what was f of s, f of s is from 0 to a, e to the minus st, f of t dt. So if I have an s here, I have an s here. If I have a 5 here, I have a 5 here. If I have 10 here, I have a tan here because S is my variable. It's the placeholder. So if I have an apple here, I have an apple here. So that means now if I have S minus A here, then I will have S minus A here. So which is basically what you get. So then this is just f of S minus A. So multiplication with an exponential in the time domain is shifting in the S domain. Just do one example for the sake of, maybe two examples for the sake of completeness, and then finish it. Right? First example, e to the 2t times t squared, and second one, and Laplace of e to the negative t times sine 2t. Okay, so let's do these things. Okay, now t squared. I know it's Laplace transform, so let's write it. 2 over s cubed. What does this thing say? First of all, you will compute the Laplace transform of this, and then you will shift s. How much? 2 to the right. So then I will just erase s, and in the place I will write s minus 2. So that's it. Okay, now this one, again, I will compute the Laplace transform of sine 2t, which is 2 over s squared plus 2 squared e to the minus t. So I will now shift it again. How much? Now this is negative, so to the left. So I will erase s. Then I will write there s minus minus 1, which is s plus 1 squared. Okay, so this is what we had. So I'm finishing. Just see, we did all, if you look at all these formulas, 1 over s minus a, all this one, and the sine version. And as you see, like the right-hand side, the things we get in the s domains are always in the rational form. They are partial fractions, basically. So that's the reason, and we know how to write partial fractions in the simplest forms, and basically that's what we are going to use. If you have some difficulties about this notion, and you please just go and check the necessary section in your calculus books for the, if you remember from the integral of partial fractions, there it helps you how to write a given rational in terms of simple partial fractions. Okay, because we are going to learn these things. All right. So this is the end of the first lecture about Laplace transforms, and we will continue with section 6.2, where basically we will start solving the differential equations by using the Laplace transform.